This video is for those of you who are taking Organic Chemistry 1, but you're studying for exam number 2. This video covers topics on stereochemistry, SN2, SN1, E1, E2 reactions, alkene reactions, and alkyne reactions. So if your exam covers those topics, you're in the right place. So let's go ahead and begin. Number 1. Which of the following represents the name of the compound shown below? So let's go ahead and name it. This is going to be carbon 1, and this is going to be carbon 2. We have a 6-membered ring, so this is cyclohexane, which we can see that in the parent name for all of the answer choices. We have a bromine on 1 and a methyl on carbon 2. So it's going to be 1-bromo, 2-methyl, cyclohexane. But what we really need to focus on in this problem is the configuration at each chiral center. We need to determine if it's R or S. So let's start with this one. Focusing on that chiral center, keep in mind a chiral center is typically a carbon with 4 different groups. So bromine is going to have the highest priority. It has a higher atomic number than carbon. Next, we have hydrogen, which is typically number 4. And then comparing these two carbons, which one is going to win? The carbon at the bottom is a secondary carbon because it's attached to 2 other carbon atoms. The carbon at the top is a tertiary carbon. It's connected to 3 other carbon atoms. A tertiary carbon will have a higher priority than a secondary carbon. So the tertiary carbon is going to be group number 2. The secondary carbon will be group number 3. And of course, H is number 4. So around the chiral center, we're going to go from 1, 2 to 3. And notice we're going in the counterclockwise direction. So that gives us the S configuration. But hydrogen, group number 4, it's not in the back, it's in the front. And we want it to be in the back when we try to figure out what the absolute configuration of the chiral center is. So we're going to have to reverse our answer. So we're going to go in the other direction, that is in a clockwise direction, which will give us R. So we have the R configuration for that chiral center. And the carbon with the bromine atom, that's carbon number 1. So it's going to be 1R, which means we could eliminate answer choices C and D. Now let's move on to the other chiral center, carbon number 2. Now let's look at the 4 different groups connected to that chiral center. So we have a hydrogen, that's going to be group number 4, and we have 3 carbon atoms to compare. So this carbon atom, let's put it in a different color. This is a primary carbon. This carbon atom here, that's going to be secondary, and this one is also secondary. But this carbon has the bromine atom, which has a higher atomic number than carbon. So this entire group will be group number 1. Comparing these two, we have a primary carbon versus a secondary carbon. The secondary carbon is going to have a higher priority. So this will be group number 2, and this is number 3. So going from 1 to 2 to 3, notice that we're going in the clockwise direction, so we get the R configuration. And H is in the back, which means we don't need to reverse it. So we're going to keep it the way it is. So for carbon number 2, the second chiral center, we have the R configuration. So the correct answer is going to be answer choice A, 1R, 2R, 1-bromo, 2-methyl cyclohexane. Number 6. Which of the following reagents will convert 3-methyl-1-butene to 3-methyl-2-butanol? So let's draw a picture. So that's butane. This is 1-butene. This will be carbon 1, 2, 3, and 4. And we have a methyl on carbon 3. So that's 3-methyl-1-butene. Here's butane. Here we have a methyl. And on carbon 2, we're going to put an OH group. So that's 3-methyl-2-butanol. So which of these reagents here will convert this alkene to that alcohol? Let's go through each one. Starting with answer choice A, we have BH3THF with hydrogen peroxide, hydroxide, and water. This reaction is called hydroboration oxidation. And what you need to know is that it proceeds with Markovnikov regiochemistry. The nucleophile, the OH group, it's going to go on the less substituted carbon of the double bond. So that is the primary carbon. Therefore, we're not going to get the answer we're looking for. So it's not answer choice A. This is the product that answer choice A will give us. Now, let's consider answer choice B. Mercury acetate with water followed by sodium borohydride. This is the oxymercuration demercuration reaction. It proceeds with Markovnikov regiochemistry without rearrangement. So the OH group is going to go on the secondary carbon. So this is the answer that we're looking for. Now you need to be familiar with the other reactions because there's a very high chance you'll see it on the exam. So looking at answer choice C, what we have is water and sulfuric acid. When these two combine, they will react and form H3O+. Now, H3O+ will react with the alkene, giving us an alcohol, but the OH group is going to go on the most substituted carbon that it can possibly get on. So this reaction can proceed with rearrangement. The end result of this reaction is that the OH group is going to go on the tertiary carbon. We'll talk about the mechanism for that later. Now, for answer choice D, once we use MCPBA, you need to know that this is a peroxy acid. The end result for this reaction is you're going to get an epoxide. Now, in the next step, when you add H3O+, the ring is going to open and you're going to get a diol. So basically 2 alcohol groups, but with anti-addition. Now this first carbon is not chiral, so we don't have to worry about the stereochemistry there. The second carbon is chiral, and so you're going to get a mixture of enantiomers. You're going to get both the R and the S stereoisomer. But let's say if you have something like this, and you were to add H3O+, the result will be, starting from the alkene, you will call that anti-addition. You're going to have one OH group in the front, one in the back. So you need to be familiar with the stereochemistry associated with that reaction. But depending on the carbon structure, you may or may not need to show it. But for a ring, you'll need to show it. So just know that this overall reaction proceeds with anti-addition. This is going to add 2 alcohols, 2 OH groups across the double bond where they're opposite to each other. Now for answer choice E, osmium tetroxide followed by sodium bisulfite with water. This too will give you a diol. The only difference is it's going to be syn addition as opposed to anti-addition. So for this reaction, you don't need to show it, but if you had, let's say, cyclohexene, and you had osmium tetroxide with the same stuff, rather than getting anti-addition, you'll get syn addition. And I'm running out of space here. Either case, these two will not give us the product that we're looking for. Now, let's focus on this reaction, but with H3O+. You need to be familiar with the mechanism for this reaction, because it's a common one. So the nucleophile, the alkene, is going to grab a proton. That proton is going to go on the primary carbon of the double bond, so we can get a more stable secondary carbocation intermediate. Now, because this secondary carbon is adjacent to a tertiary carbon, we're going to get something known as a hydride shift. So we're going to get a carbocation rearrangement. The driving force for that rearrangement is going to be increased carbocation stability. So now we're going to have a tertiary carbocation, and then water is going to react with it. Now, we don't need to worry about the stereochemistry here because this carbon is not chiral. And then we're going to use another water molecule to remove this hydrogen. So the end result is that we're going to get a tertiary alcohol, 2-methyl 2-butanol. Number 13. What is the major substitution product of the reaction shown below? So we have an alkyl halide reacting with methanol. What mechanism will this reaction most likely occur by? Now what we have is the secondary alkyl halide. The carbon that has the bromine atom is attached to two other carbon atoms. Methanol is a protic solvent. So the fact that we have a secondary alkyl halide and a polar protic solvent, this is going to favor the SN1 reaction over the SN2 reaction. Now the SN1 reaction typically occurs with the E1 reaction. However, we're not focused on the major elimination product. We want to find the major substitution product. So we're not going to worry about the E1 mechanism. We're going to focus on the SN1 mechanism. But you should know that these two, they occur together. And temperature will favor E1 over S1 if you increase the temperature. So if you raise the temperature, the yield of the S1 product will go down, and the yield of the E1 product will go up. So you'll get more of the substitution product at low temperatures, but more of the E1 product at higher temperatures. Now, for us to find the major product for this reaction, we need to write out the mechanism. In the first step for an S1 reaction, the leaving group is going to leave. And so we're going to get a secondary carbocation, which is adjacent to a tertiary carbon. So a rearrangement will happen here. But notice that we have an unstable 4-carbon ring. When you see that, look out for ring expansions. A 4-carbon ring can easily expand to a 5-carbon ring, depending on the carbon structure, and sometimes you'll see a 5-carbon ring expand into a 6-carbon ring. 6-carbon rings have minimal ring strain or angle strain, so they tend to be pretty stable. If you have a 6-carbon ring, it's rare that you'll get another ring expansion or ring contraction. So what's going to happen here, one of these bonds are going to break. But let's number the carbon atoms. Let's call this carbon 1, 2, 3, 4, 5. So we can break the bond between carbon 2 and 5 or carbons 2 and 3. It doesn't matter. But let's break the bond between carbons 2 and 5. So the electrons that connects carbons 2 and 5, those are going to be used to connect carbons 1 and 5 together. So we're going to get a 5 carbon ring. Let's call this carbon 1, 2, 3, 4, and 5. Now, carbon 1 has a methyl group. Carbon 2 and 5, they lost the bond. But carbons 1 and 5, they gained the bond. Carbon 5 got the bond back. Carbon 1 gained a bond. Carbon 2 lost the bond. It didn't get any back, so carbon 2 will have the positive charge. So right now, we still have a secondary carbocation intermediate. So we're going to get another carbocation rearrangement. This secondary carbocation is next to a tertiary carbon, so we're going to get a hydride shift. Once the hydrogen moves, we're going to get a plus charge on this carbon. So now we have a tertiary carbocation with a 5 carbon ring. So this carbocation is much more stable than this one. So now that we have the most stable carbocation that we can get for this structure, the solvent is going to behave as a nucleophile, reacting with the carbocation. When the solvent is the nucleophile, the reaction is known as a solvolysis reaction. This reaction is typically associated with an SN1 reaction, but sometimes you'll see it with an SN2 reaction. But for the most part, if you see solvolysis, 80 to 90% of the time it's an S1 reaction. But that's when the solvent behaves as a nucleophile in the substitution reaction. So now we have an oxygen with a hydrogen and a methyl group. Now the next step is going to be a proton transfer step, or an acid-base reaction. So notice the difference between how methanol is behaving in this step and how it will behave in this step. In this step, methanol is acting as a nucleophile. It's reacting with the electrophilic carbocation. But here, it's going to act as a base, in that it's going to abstract a proton, because that's what bases do. So that's the difference between a base and a nucleophile. Bases, they go for protons, they abstract hydrogen atoms. Nucleophiles, in the context of organic chemistry, they typically react with electrophilic carbon atoms. So the end result is that we get an ether. So this is 1-methoxy, 1-methyl, cyclopentane. So that's the major product for this reaction. 21. Which of the following statements is not true? The rate of an SN2 reaction will double if the concentration of the nucleophile doubles. Is that true or false? We know the rate law expression for an SN2 reaction is that the rate depends on the concentration of the substrate and the concentration of the nucleophile. And this is raised to the first power. So if the concentration of the nucleophile doubles, we'll put a 2 for that. That means that the concentration of the substrate stays the same, so we'll put a 1. K is a constant, so we don't need to worry about that. 1 times 2 is 2. The rate is going to double. So answer choice A is a true statement. We're looking for the false statement. So answer choice A is not our answer. Now let's look at answer choice B. The rate of an E1 reaction will triple if the concentration of the alkyl halide triples. Is that true or false? For an E1 reaction, the rate only depends on the concentration of the substrate. It doesn't depend on the concentration of the base. Now, if we triple the concentration of the substrate or the alkyl halide, the rate is going to triple. So B is the true statement. We can eliminate that answer choice. Moving on to C, the rate of an E2 reaction will increase by a factor of 6 if the concentration of the alkyl halide doubles and the concentration of the base triples. We know that for an E2 reaction, the rate depends on the concentration of the substrate and the concentration of the base. So if we double the concentration of the substrate or the alkyl halide and we triple the concentration of the base, 2 times 3 is 6, the rate will increase by a factor of 6. So C is a true statement. Looking at answer choice D, the rate of an SN2 reaction will quadruple if the concentration of the nucleophile quadruples. True or false? The rate for an S1 reaction doesn't depend on the concentration of the substrate. It only depends on the... Let me say that again. The rate of an S1 reaction doesn't depend on the concentration of the nucleophile. It only depends on the concentration of the substrate. So this is the rate law expression for an S1 reaction. The nucleophile is not in it, as you could see. As a result, it doesn't matter what we do with the concentration of the nucleophile. If we double it, if we triple it, it will have no impact on the rate of an S1 reaction. So this is the false statement, which means D is the answer we're looking for. Now let's talk about why. Let's say we have tert butyl bromide and we're reacting it with water. So we have a tertiary alkyl halide, a protic solvent, that's going to favor an S1E1 reaction. But we'll focus on the S1 reaction. The leaving group is going to leave. That's the first step. This step is the slow step. The second step is fast. That's when the solvent, which acts as a nucleophile, reacts with the carbocation, giving us this intermediate. Now the rate for the overall S1 reaction doesn't depend on the fast step, it depends on the slow step. And notice the nucleophile is not part of the slow step, only the substrate is. That's why the rate for an S1 reaction and also an E1 reaction doesn't depend on the concentration of the nucleophile or the base. It's because they're not involved in the first step, which is the slow step or the rate determinant step. That's why it only depends on the concentration of the substrate. So that's it for 21. The correct answer is answer choice D. Now, let's move on to 34. Which of the following reagents will convert 1 butene to 2 butanone? So let's draw a picture. So here we have 1 butene. We can see we have a total of 4 carbon atoms. The alkyne is on carbon 1, or between carbons 1 and 2. And we need to convert it into 2-butanone. How can we do this? How can we get the carbonyl group on this carbon here? Well, let's go through each reaction. So first we have hydrogen gas with a palladium catalyst. This will convert the alkyne all the way to an alkane. Of course, you'll need 2 equivalents, but it's not going to stop at the alkene level. For the next reaction, we have solid lithium metal and liquid methylamine. Now, that reaction is very similar to this reaction, where you have solid sodium metal and liquid ammonia. This reaction will convert an alkyne into a transalkene, but because we're dealing with a terminal alkyne, we're going to get a terminal alkene, and cis and trans doesn't really apply for that. Now, methylamine and ammonia, they're very similar. The only difference is, instead of having 3 hydrogen atoms on the nitrogen, one of them has been substituted with a methyl group. But the end result is going to be the same. We're going to get an alkene. Now, for the next one, we have hydroboration oxidation, but with an alkyne. We have R2BH, which works very similar to BH3. And in the second step, we have oxidation, hydrogen peroxide with sodium hydroxide. Now, what's going to happen is this reaction is going to proceed with anti-Markovnikov-Regio chemistry. Initially, it's going to convert the alkyne to an alkene, but this is also a hydration reaction. We're going to get an OH group, but on the less substituted carbon atom of the triple bond. So this carbon is primary, this one is secondary. The OH group is going to be on the primary carbon. So this is called an enol. We have an alcohol and an alkene. Now the enol, it's not very stable relative to what it can convert to. There's an equilibrium in this reaction here, but it's going to quickly convert to an aldehyde. So this is known as tautomerization, where the enol can convert into an aldehyde or a ketone. Now for answer choice D, we have mercury sulfate with sulfuric acid and water. So think of this reaction as H3O+, where it's an acid catalyzed hydration, but mercury acts as the catalyst for this reaction. So it's kind of similar to the oxymercuration demercuration reaction, but somewhat different. This reaction proceeds with Markovnikov-Regio chemistry. It's very similar to this one. We're going to get an enol, but the difference is the OH group is going to go on the more substituted carbon. In this case, the secondary carbon. And that enol is going to tautomerize into a ketone. And this is the product that we want, 2-butanone. So the correct answer for this problem is answer choice D. 43. What is the major product of the reaction shown below? So we have a molecule that has 2 functional groups, an alkene and an alcohol. Whenever you see that, when there's multiple functional groups in a molecule, pay attention for intramolecular reactions. Now we know that the alkene can react with bromine. We've seen how those two react. There can also be side products as well. This oxygen could react with bromine, but since we haven't seen that reaction in this type of content in organic chemistry, we're not going to touch that. But we do know that bromine will react with the alkene. The double bond is going to attack bromine, and bromine is going to attack the double bond simultaneously, kicking out this bromide ion. And so we're going to get a cyclic bromonium ion. Now here we have a secondary carbon, and here we have a tertiary carbon. The tertiary carbon is going to have more partial positive charge than the secondary carbon. And so this oxygen, which has a partial negative charge, is going to be attracted to the partially positive tertiary carbon. So it's going to attack that carbon. This bond is going to break. Those electrons will go to the bromine atom. And so this is going to close and form a ring. We'll call this atom 1, 2, 3, 4, 5, 6. So we're going to have a 6-membered ring. With an oxygen atom being part of it. Now, on carbon 6, we have an ethyl group here. And carbon 6 also has a methyl group. So here is the methyl group, and this is the ethyl group. Now, on the ethyl group, this bond is broken, so carbon 6 is not directly attached to a bromine. But this carbon, the first carbon in the ethyl group, still has a bond to a bromine atom. So that's what we now have, but we still have this hydrogen atom on the oxygen that we need to deal with. Now, we could use another molecule like this with an OH group to remove the hydrogen. We could use bromide or something else. I'm just going to put a generic base. So a generic base is going to remove this hydrogen and put a lone pair on that oxygen. There's already one, but it's going to have two. So this is going to be the final product for this reaction. So that's what we're going to get in this reaction. By the way, if you like this video and if you think it's helpful, feel free to share it with your fellow classmates. If you know of any other students who might be struggling with this topic, feel free to text it or email it to them, whichever is convenient. And feel free to share it on Facebook, Twitter, Pinterest, Instagram, or any other social media platform that you might enjoy using. But now let's get back to the video. 51. What is the major product of the following reaction? So here we have 2-bromo-4-fluoropentane, and we're going to react it with potassium cyanide, and the solvent of choice is hexamethyl phosphoramide, HMPA. When you think of an amide is basically a carbonyl group attached to a nitrogen. A phosphoramide is very similar, but instead of a carbon, we have a phosphorus group. So that's a phosphoramide. Now think of the word hexamethyl. We got 6 methyls. We can put 2 methyls on this nitrogen. And if we add 2 more nitrogen atoms, we can have a total of 6 methyls. So this is hexamethyl phosphoramide. We got 6 methyls and a phosphoramide group. So this is a polar aprotic solvent. That's what you need to know when you see HMPA. So we have a secondary alkyl halide with 2 halogens. We have a good nucleophile, cyanide, and we have a polar aprotic solvent. These conditions favor an SN2 reaction. Now, notice that we have 2 leaving groups, fluoride and bromide. Which leaving group is better? with the halogens, we know that leaving group stability increases as you go down the group. So iodide is the best leaving group out of the halogens, but comparing bromide and fluoride, bromide is a better leaving group. Fluoride is the poor leaving group. So cyanide is going to preferentially attack the carbon with the better leaving group. So we're going to kick out the bromine, and we're going to get this. Now, because we're dealing with an SN2 reaction, we're going to have inversion of stereochemistry. Well, first I got to get rid of the bromine. Let's put cyanide instead. The fluorine is going to remain. It's not easy to kick out a fluorine group because it's a poor leaving group. But this is going to be the major product. So we just got to replace bromine with cyanide and with inversion of configuration. So that's the answer for 51. Number 60. Which of the following molecules is chiral? Alright, let's go through each one. So looking at answer choice A, notice that we have a line of symmetry. We can see the bromine atoms are the same across that line and are on the same side. Also, there are no chiral centers here. This carbon is not chiral because the left side is the same as the right side. So for answer choice A, this is an achiral molecule. Achiral molecules are optically inactive. Now looking at answer choice B, we do have a plane of symmetry, and we can see it right here. The left side is the same as the right side. So this is going to be an achiral molecule. For answer choice C, we have an allene. Now for allenes, what you want to do is look on each side. On the right side, we have two different groups. On the left side, we have two of the same groups. If one of the sides have two identical groups, it's going to be achiral. In order for it to be chiral, the right side has to have two different groups and the left side has to have two different groups in order for it to be chiral. Now for answer choice D, notice that we don't have a plane of symmetry. The left side is not the same as the right side. So this is going to be this molecule is chiral, which means it's optically active. So D is the correct answer for this problem. 78. What is the major product of the reaction? So we have 1-methylcyclohexene with hydroboration oxidation. Now we know this reaction proceeds with anti-Markovnikov regiochemistry. In the first step, the alkene is going to react with BD3. The double bond attacks boron, and deuterium attacks the double bond as well. So initially, BD2 adds to the less substituted carbon. Deuterium, which is taking the place of hydrogen, is added to the more substituted carbon. But these two, they're added on the same side with syn addition. Now, when you add step 2, hydrogen peroxide and hydroxide, this gets replaced with an OH group from hydrogen peroxide. This hydroxide simply removes the hydrogen from hydrogen peroxide, but the OH group that this will be replaced by comes from the hydrogen peroxide. It's important to know that in the event that you have D2O2, because then this group will be OD instead of OH. So the OH group and deuterium, they're going to be on the same side, syn addition, which means methyl has to be on the other side. So the first thing we want to look for is we want to make sure that the OH group is on the less substituted carbon. we could eliminate answer choice B. Actually, no. We can eliminate answer choice C. The OH group is on the tertiary carbon, and we can eliminate answer choice D. Now, we're between A and B. The OH group is on the less substituted secondary carbon. Now, looking at deuterium and the OH group, they have to be on the same side because this is syn addition. Here, we see them on the same side. Here, they're on opposite sides, anti. So we can eliminate answer choice B. Therefore, answer choice A is the correct answer. We need to make sure that deuterium and hydroxide are on the same side. And hydroxide is going to be, or the hydroxyl group is going to be anti with respect to the methyl group, but syn with respect to deuterium. 81. What is the major product of the reaction shown below? So notice that this reaction is stereospecific. Hydroxide has to grab the hydrogen that's one carbon away from the bromine. Now notice that we only have one hydrogen. If there were two hydrogen atoms, we would get a mixture of products. We can get more than one product. But because there's only one hydrogen that the hydroxide base can abstract, we're going to get one particular stereoisomer. So if there were like two hydrogen atoms here, we can get both the cis and the trans isomer, the E and Z isomers. But because we have one, we're going to get one of the E or the Z isomers, so not both. So be mindful of that. So the base is going to grab the proton. We're going to form a pi bond and kick out the leaving group. The good thing about this problem is that the hydrogen and the bromine atom, they were already anti with respect to each other. So we don't need to change anything. We don't need to rotate the molecule. So we're going to get a double bond. Notice that the methyl groups, they're on the same side. They're on different carbons, but on the same side. And after the E2 reaction, they will continue to remain on the same side. So we have a hydrogen on this side left over, and the ethyl group on the other carbon. So this is going to be the major product. So comparing ethyl and methyl, ethyl has a higher priority. Comparing methyl and hydrogen, hydrogen has a higher priority. So the two high priority groups, they're on opposite sides of each other. So therefore we have the E isomer. So that's the major product for this particular reaction.